Welcome to section 3.5, properties of rational functions. All right, let's first define a rational function. So a rational function is a function of the form r of x equals p of x divided by q of x, where p and q are polynomial functions and q is not the zero polynomial. The domain of R is the set of all real numbers except those for which the denominator Q is 0. For our first set of examples, we're going to find the domain of a rational function. So keep in mind that a rational function is set up like a fraction. So when we're trying to find the domain of these functions, we want to find the x values that do not exist in our function. So the denominator of a fraction we know cannot equal 0 or it will be undefined. So any x values that make our denominator 0 would not be considered in the domain. So we're going to set all of our denominators equal to 0 to determine the x values that make our function undefined. So in our first function here, r of x equals 3x squared minus 5 divided by x plus 2, we're going to set our denominator x plus 2 equal to 0 and solve for x. And we get x equals negative 2. That means the domain is going to be all real numbers of x except for when x equals negative 2. Because when x equals negative 2, then our denominator is 0, making our rational function undefined. For b, we have r of x equals 1 divided by x squared minus 25. So we'll set x squared minus 25 equal to 0. This is the difference of squares. So when we write this in factored form, we'll have x minus 5 times x plus 5 equals 0. So we can then use the zero factor property by setting each factor equal to 0 and solving for x. So x equals negative 5 and, x equals positive 5 and x equals negative 5. But the first one is a positive 5. And then this one is negative 5. There we go. So the domain is going to be all values of x except for when x equals 5 and x equals negative 5. Alrighty. For c, we have r of x equals 2x cubed divided by x squared plus 1. Okay. So when we plug in any value for x, whether positive or negative or even 0, we can see here that our denominator will be positive. Okay. The only thing here that could potentially make this negative is an imaginary number, but we want only the real numbers. So this is going to be the set of all real numbers. Okay, so we can give it the symbol for all real numbers, or we can say from negative infinity to infinity, or the set of all real numbers. Okay. For d, we have r of x equals x squared minus 4 divided by x minus 2. So we'll set our denominator equal to 0 to determine the x value that would make our denominator 0, and that would be 2. So the domain for this function would be all x values except for when x equals 2. Excellent. So if r of x equals p of x divided by q of x is a rational function, and if p and q have no common factors, then the rational function r is said to be in lowest terms. Warning, the domain of a rational function must be found before writing the function in lowest terms. So when we eventually get to the point where we're going to be graphing rational functions, we first want to find the domain of our rational function before we start simplifying our function. Okay. All right, so let's graph h of x. H of x is a rational function, 1 divided by x squared. And then we're going to look at this graph a little bit more once we have plotted our points. All right, so we have a table here. We have our x coordinates in the first column. And so in the second column, we are going to have our y coordinates. And our y coordinates here represent h of x. Okay. So when we take each x value and we substitute it into our function h of x, what would be the value we would get? Okay. So when we substitute in 1/2 in for x, all right, so we'll evaluate h when x is 1/2. We are substituting in 1/2 for x and then simplifying. So when we simplify this ratio, we'll get the value 4. When we do the same thing for 100, we would get 10,000. When we do the next for 1 divided by 10,000, we'll get 100 million. Okay. Then when we substitute in 1, we'll get 1. Substitute in 2, we'll get 1/4. Substitute in 100, we'll get 1 over 10,000. We substitute in 10,000, we'll get 1 over 100 million. Okay. Now, if you needed assistance with this, you can utilize your calculator by entering in your expression and then simplifying it. Okay. So we have our points, but let's actually graph this to visually see what is happening in our graph. All right, so we have our calculator here, and we are going to enter in our function. So y equals, I want a fraction, so I'll press alpha x. So then I have 1 divided by x squared. Enter that in. I'm going to press graph to see what it looks like. Okay. So I see here that I have a line in my second quadrant and a line in my first quadrant. So I want to see that just a little bit clearer so that it helps that my calculator matches the graph on my notes. So I'm going to go to Window, and my x min is -5. My x max is 5. It's going by a scale of 1. My y min is going to be 1, -1. My y max is going to be 4, and it's going by a scale of 1. So now I'm going to press graph, and I now have an image that's going to be similar to the one that I'm going to graph here. Okay. So I'm going to give a rough sketch of this graph, and then we're going to analyze it a little bit more. Okay. So some points that I have here are 1, 1, and I have 1/2, 4. Okay. And then I have 2 1/4. Now on my calculator here, I see kind of a mirror image on the left-hand side. So my x coordinates are negative, but my y coordinates are the same. Okay. So I'll have negative 2 1/4. I'll have negative 1 1. And I'll have negative 1/2 4. So then we can plot these points and connect our dots. There we go. And just for our reference, I'm going to label my points. And this is 1 1. This is 2 1/4. Negative 2 1/4. Negative 1 1. Negative 1/2 4. Alrighty. So notice here that as x is approaching infinity, okay, so as x is approaching infinity, the y values are approaching 0 because they never cross the x-axis. Okay, so as x is approaching infinity, our y, which is h of x, is approaching 0. As x approaches negative infinity, so that's in this direction, so as the x values get smaller and smaller, h of x is also approaching 0. Okay. All right. But now as x approaches 0, so in the opposite direction, as x approaches 0, so it's going towards the origin, whether it's from the left or the right, right? H of x is approaching infinity because the arrows up here are increasing. Okay, so in calculus, we would say the limit as x approaches 0, h of x is approaching infinity. All right, so the domain of this function, okay, so this is our analysis. The domain of this function is going to be all x values except for when x equals 0. And we know that because if we set our denominator equal to 0, we'll get x equals 0. And so 0 cannot be an x value for h of x because it would make the rational function undefined. And so in our graph, we visually can see that because our graph does not cross the y-axis. Okay. All right, so now we're going to use transformations to graph a rational function. So we're going to first start off with our original function, y equals 1 divided by x squared, and then apply transformations in order to get our rational function r of x. Okay. So we're going to start off with our original function, y equals 1 divided by x squared. So we know that we have some points like 1/2 4, 1 1, and 2 1/4, and then their mirror images. Okay, these are the same points that we plotted in the previous problem. I'm going to connect my dots. Rough sketch. Rough sketch. Okay. All right. Now I'm asked to graph y equals 1 divided by the quantity x plus 1 squared. So here we are replacing, so we replace x by x plus 1. Okay, so in doing that, we are shifting left by 1 unit. Remember, when you add a value to your x coordinate, you're going in the opposite direction of your sign. So if I'm adding 1, the opposite of that would be subtracting 1. So I'm going to the left 1. Okay. So if I'm going to the left 1, my original point 1, 1 is now going to be 0, 1. So all of my x values are moving to the left, but my y values stay the same. Okay, so 2 1/4 is now 1 1/4, and then 1/2 4 is now, so if I'm subtracting 1 from 1/2, I'll have negative 1/2 4. Okay, before, my mirror line of symmetry was y equals 0. So since I'm moving to the left 1, it's now going to be negative 1. So let's just draw a dashed line for now, because this will help me in graphing this rational function. So now I'll have 1 1/4 4. I'll have 2 1, and I'll have 3 negative 3 1/4. Okay, so just to let you know here, I have negative 2 1, negative 3 1/4, and then 1 and 1/4, negative 1 and 1/4, and 4. There we go. Those are those points. Okay, and then these ones, 0 1, 1 1/4, and this value is negative 1/4 4. There we go. Awesome. Okay, so our next transformation, okay, gives us our function r of x, 1 divided by the quantity x plus 1 squared minus 2. So the only difference between these two is subtracting 2. So if we're subtracting 2, we're going to now go down 2 units. So this affects our y. Okay. So now we're going to take these points and we're going to shift them down 2 units. So in shifting down, let's start at 0 1. We're going to now go down 2. So that's going to be this point right here. And that's negative 1 0. Okay. Moving it down 2 units. Then if we take the point 1 and 1/4, moving down 2 units, that would be, let's see. Okay, we'll be affecting our y coordinate. So we'll be at 1, and then we go down 2. So we'll be at 1 and 3/4. So 1, negative 1 and 3/4. Okay, so negative 1. Oh, nope, that's for the y, not for the x. The x stays the same. It's only affecting our y. Wrote that in the wrong spot. Okay, so we have 1 and negative 1 3/4. There we go. Okay. And then our next was originally negative 1/4 and 4. So if we're subtracting 2, it would be negative 1/4, 2. Okay. Negative 1/4, 2. There we go. Note that our line of symmetry here is still the same. So it hasn't moved because we did not affect our x coordinate in this transformation. So it's still at negative 1. Okay. Now we can do the same thing on the left side. So we would have to subtract 2 from all of the y coordinates on that side as well, noting that the x coordinates will stay the same. Okay. Next point is going to be negative 1 1/4, 2. And then we're going to have negative 2, negative 1. And then we'll have negative 3 and negative 1 3/4. Okay. So then we can connect our dots. Note that in our first two graphs here, as x is approaching negative infinity and positive infinity, y is approaching 0. So it does not cross y equals 0 or the x-axis. Since we have now shifted our graph down 2 units, that line that it's approaching has now shifted down 2 units. And so now our graph is approaching negative 2. So as x is moving to positive infinity or negative infinity, y is approaching negative 2. All right. Now these dashed lines that I created actually have a name. And that name is called asymptotes. So the dashed horizontal line, y equals negative 2, and the dashed vertical line, x equals negative 1, that we drew in the previous example are called asymptotes of the graph r of x equals 1 divided by the quantity x plus 1 squared minus 2. Okay. All right. The definition of our horizontal and vertical asymptotes. So we drew horizontal and vertical asymptotes. So let's dive a little bit deeper into their definitions. So we're going to let r denote a function. Okay. If x, or if as x approaches negative infinity, or as x approaches infinity, the values of r of x approach some fixed number L. Then the line y equals L is a horizontal asymptote of the graph of r. Okay, so we're going to refer to the images here in A and B, both representing a graph that have horizontal asymptotes where y equals L. Okay, so as x is approaching negative infinity or as x is approaching infinity, y is approaching a fixed value L. Okay. If as x approaches some number c, where the absolute value of r of x approaches infinity, that is, r of x is approaching negative infinity or r of x is approaching infinity, then the line x equals c is a vertical asymptote of the graph of r. And for this, we're going to refer to the images in C and D. So we say absolute value of r of x because r of x could be negative or positive. So as r of x is approaching negative infinity or r of x is approaching infinity, the line x equals c is our vertical asymptote. Okay. Alrighty. So as x is coming or approaching from the left, or as x is approaching from the right, r of x is approaching infinity or negative infinity, then we know we have a vertical asymptote at a point C. Okay. So in summary, a horizontal asymptote, when it occurs, describes the end behavior of the graph as x is approaching negative infinity or as x is approaching infinity. So the graph of a function may intersect a horizontal asymptote. Now, a vertical asymptote, when it occurs, describes the behavior of the graph when x is close to some number c. So the graph of a rational function never intersects a vertical asymptote. Okay? There is a third possibility as well. So if as x approaches negative infinity or as x approaches infinity, the value of a rational function r of x approaches a linear expression, ax plus b, where a does not equal 0, then the line y equals ax plus b, where a does not equal 0, is an oblique or slant asymptote of r. So the figure here to the right shows an oblique, it's a hard time saying that word, oblique or slant asymptote. And an oblique or slant asymptote, when it occurs, describes the end behavior of the graph as well. So the graph of a function can intersect an oblique asymptote. So between the three, the vertical asymptote is the only asymptote where the graph never intersects that line, whereas a horizontal or slant oblique asymptote are areas in which your graph could still intersect. Okay, so think of asymptotes as lines. Okay, so that means they must have an equation. All right, so for your oblique and slant asymptotes, they'll be in the form y equals ax plus b. For your vertical asymptotes, they'll be in the form of x equals c. And for your horizontal asymptotes, they'll be in the form y equals L. Okay. Objective 2. Find the vertical asymptotes of a rational function. So locating vertical asymptotes. Now the graph of a rational function, r of x equals p of x divided by q of x in lowest terms, has a vertical asymptote x equals r if r is a real zero of the denominator q. That is, if x minus r, which is a factor of the denominator q of the rational function r in lowest terms, the graph of r has a vertical asymptote x equals r. Warning, if a rational function is not in lowest terms, then this theorem may result in an incorrect listing of a vertical asymptote. So we know when we are given a rational function, the first thing we do is find the domain. And then after that, we will then put it in lowest terms. We can put it in lowest terms, which will then help us identify what our vertical asymptote is. Okay. All right, so let's find some vertical asymptotes of these functions. So the first one is f of x equals x plus 5 divided by x minus 3. So remember, our theorem here says that if our rational function is in lowest terms, then we could potentially have a vertical asymptote where x equals r, where r is a real zero, of the denominator of q. So that means we're going to take the factor in the denominator, set it equal to 0 in order to find our vertical asymptote. So for a, we have f of x equals x plus 5 divided by x minus 3. So our denominator here is x minus 3. And we also see here that our f of x is written in lowest terms, meaning there are no factors that we can eliminate. So we're going to take x minus 3, set it equal to 0, and we get x equals 3. Okay, so x equals 3 would be our vertical asymptote for this function. For b, we have r of x equals x divided by x squared minus 49. Now, our denominator here is x squared minus 49. All right, we know x squared minus 49 is written as the difference of squares. So this could also be written as x divided by x minus 7 times x plus 7. Okay, so making sure that it's written in lowest terms, which it is. There are no factors that we can cancel. So we are going to set our denominators equal to 0. And I say denominators, which is incorrect. The denominator that contains factors, so that would be plural. So we would have x minus 7 equals 0 and x plus 7 equals 0. So we would get x equals 7 and x equals negative 7 as our two vertical asymptotes. For c, we have x squared divided by x squared plus 9. All right, so now we need to simplify this. X squared plus 9 is not the difference of squares. It's actually a sum of squares, and there is no factored formula for the sum of squares. So what we could do in order to find our vertical asymptote is to set this equal to 0 to find r. So we would get x squared equals negative 9. Okay, and then we take the square root. So we get plus or minus the square root of negative 9. And so x would equal plus or minus 3i. Okay, so that's an imaginary number. So we know then that this rational function has no vertical asymptote. And I'm just going to abbreviate that VA. Okay, because we're working in the real number system, so we're not graphing complex values like 3i. So we know that there is no vertical asymptote for this function. All right, D, g of x equals x squared minus 25 divided by x squared plus 2x minus 35. Now, the difference between this function and the other three is that our polynomial in the numerator and denominator can both be factored. So in order to determine whether this function is written in lowest terms, we're going to need to factor both the numerator and denominator. So the numerator, x squared minus 25, is the difference of two squares. So we will have x minus 5 and x plus 5 as our factored form. Then in the denominator, we have a quadratic. This quadratic can be factored. When it is factored, we have the factors x plus 7 times x minus 5. Okay, so now that we have the numerator and denominator in factored form, we can simplify. So we can simplify rational functions by eliminating common factors that we see in the numerator and denominator. In this function, I see that the numerator and denominator both have the factor x minus 5. So if I were to simplify this ratio, I would have x plus 5 in the numerator and x plus 7 in the denominator, which would cancel out the x minus 5 factors. Now that it's written in lowest terms, I can now find my vertical asymptote by setting the denominator equal to 0. So I have x plus 7 equals 0, and so I get x equals negative 7 as the vertical asymptote. Note that us setting the denominator equal to 0 helps to identify not just the vertical asymptote, but also the x value that is not considered in our domain. Okay. All right. So multiplicity and vertical asymptotes. So a rational function in lowest terms, the multiplicities of the real zeros in the denominator can be used to determine the behavior of the graph around each vertical asymptote. So consider the following 4 functions, each with a single vertical asymptote x equals 2. So our graph is approaching x equals 2, but never crosses. So in A here, we have an odd multiplicity. Note that as x is approaching 2 from the left, right, our y, or our r of x, is approaching negative infinity. Now, as our graph is approaching 2 from the right, then our y is approaching infinity. So it's going in opposite directions as it's approaching our vertical asymptote. This is an odd multiplicity. Another representation of odd multiplicity is kind of the reverse of that. So as x is approaching 2 from the left, your y is approaching infinity, or as x is approaching 2 from the right, your y is approaching negative infinity. Again, as it's approaching your vertical asymptote, from either side, the direction of y is opposite. So one's going to positive infinity and one's going to negative infinity. When this happens, you can state that there is an odd multiplicity at this value. Now for even multiplicity, okay, as x is approaching 2 from the left, your r of x, y is approaching infinity. And as it's approaching 2 from the right, your y or r of x is approaching infinity. So whether it's coming from the left or whether it's coming from the right, your y is approaching in the same direction. Similarly to D, approaching from the left or the right of x towards 2, our y is approaching negative infinity. And when you see this represented in your graph on a rational function, you can then state that there is an even multiplicity at that value. Okay. So let's write this in conclusion. We can make the following statements. If the multiplicity of the real zero that gives rise to the vertical asymptote is odd, the graph approaches infinity on one side of the vertical asymptote and approaches negative infinity on the other side. If the multiplicity of the real zero that gives rise to the vertical asymptote is even, the graph approaches either infinity or negative infinity on both sides of the vertical asymptote. Okay. All right, objective 3, we're now going to dive in a little deeper into horizontal and oblique asymptotes. So to find a horizontal or oblique asymptote, we need to know how the function behaves as x approaches infinity or as x approaches negative infinity. That is, we need to determine the end behavior of the function. And this can be done by examining the degrees of the numerator and denominator. Remember, degree is the highest power of a polynomial. So let's consider a rational function where we have p of x divided by q of x. So we have 2 polynomial functions, one in the numerator and one in the denominator. We're going to give the degree of the numerator n and the degree of the denominator m. Okay, so the degree of the numerator is going to be n. The degree of the denominator is going to be m. So if n is less than m. Okay, so the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is going to be our horizontal asymptote. Okay. If n equals m, then the degree of the numerator equals the degree of the denominator. The line y equals a sub n divided by b sub m is a horizontal asymptote. Okay, so a sub n is going to be the leading coefficient of your polynomial in the numerator, and b sub m is going to be the leading coefficient of your polynomial in the denominator. Okay, so it's going to be the horizontal asymptote is going to be the ratio of the leading coefficients. Okay, so if n is less than m, your horizontal asymptote is y equals 0. If n equals m, your horizontal asymptote is going to be the ratio of your leading coefficients. If n equals m plus 1, okay, so that's the degree of the numerator is 1 more than the degree of the denominator, then the line y equals ax plus b is an oblique asymptote. Okay, so this is going to be found by identifying the quotient using polynomial division. Okay, so if n equals m plus 1, then you have an oblique asymptote, and you need to find that equation by performing polynomial division. So you're dividing that top polynomial by the denominator. If n is greater than or equal to m plus 2, so that means the degree of the numerator is 2 or more greater than the degree of the denominator, then there is no horizontal or oblique asymptotes. Okay, and the end behavior of the graph resembles the power function, where y equals the ratio of the leading coefficients times x to the power n minus m. Okay, note that a rational function never has both a horizontal asymptote and an oblique asymptote. Okay, a rational function may have neither a horizontal nor an oblique asymptote, but they can't have both. All right, so now let's find some asymptotes. So here we're asked to find the horizontal asymptote if one exists for this graph r of x equals 3x to the fourth minus 2x cubed minus x divided by x to the sixth plus 4x squared plus 8. Okay, so first we need to find our degrees. So we know our rational functions are written as r of x equals p of x divided by q of x. Okay, so p of x has a degree of 4, and q of x has a degree of 6, because those are the highest powers in each polynomial. So I know then that n equals 4 and m equals 6. All right, so n is less than m because 4 is less than 6. Since 4 is less than 6, I know my horizontal asymptote, which I will abbreviate HA, is going to be the line y equals 0. Okay. Alrighty. For this example, we're asked to find the horizontal or oblique asymptote if one exists for the graph of h of x, 2x cubed plus 3x squared plus 2 divided by x squared plus x plus 1. Okay, so we have a visual here. And so we know that we are going to have an oblique asymptote, but we're going to confirm that using our definitions that we just found for finding horizontal and oblique asymptotes. And we're going to confirm what we see here in the graph. So we know p of x, which is a polynomial of our numerator. I don't want an equal sign. Has a degree of 3. And q of x, which is the polynomial of our denominator, has a degree of 2. So that means n equals 3 and m equals 2. Okay? So notice that n is 1 more than m, because 3 equals 2 plus 1. Since 3 equals 2 plus 1, we know that there's going to be an oblique asymptote of the form y equals ax plus b, where a does not equal 0. So to find this equation, we're going to have to divide our rational function, okay, using polynomial division. So we'll have x squared plus x plus 1. And then we'll have 2x cubed plus 3x squared plus 0x. I need a placeholder for x plus 2. Okay. All right. So first I'm going to divide 2x cubed by x squared. So what factor times x squared will get me 2x cubed, and that's going to be 2x. So 2x times x squared will get me 2x cubed. 2x times x will get me 2x squared. 2x times 1 will get me 2x. So now I'm going to subtract that from my first terms. So 2x cubed minus 2x cubed is 0. 3x squared minus 2x squared is 1x squared. 0x minus 2x is minus 2x. And then I can bring down the 2, my constant term. So now I'm going to divide x squared by x squared, and that's going to get me 1. So 1 times x squared is x squared. 1 times x is x. 1 times 1 is 1. So I'm going to subtract this polynomial. X squared minus x squared is 0. Negative 2x minus x is going to be negative 3x. Okay. Then I have 2 minus 1. 2 minus 1 is positive 1. Okay. And so I now am going to divide negative 3x by x squared. And I don't have a factor to add. So I know then that negative 3x plus 1 is my remainder. Okay, so this is my r of x. My oblique asymptote is going to be the quotient of my polynomial division, which is q of x. Q of x in terms of the polynomial division. So the q of x here and the q of x that's a part of our rational function represent two different things. Just wanted to note that because there is two different q of x's on our screen. All right, so the q of x here that I'm referring to is the quotient. And the r of x here is the remainder. All right, so our oblique asymptote is going to be the equation y equals 2x plus 1. Awesome. All right, our next example, we need to find the horizontal or oblique asymptote, if one exists, of this function r of x equals 9x squared minus x plus 1 divided by 3x squared minus 2. So let's first find our degrees. So p of x has a degree of 2. Q of x has a degree of 2. So n equals 2 and m equals 2. So n equals m because 2 equals 2. Since n and m equal each other, the horizontal asymptote exists for this function. And the line for our horizontal asymptote is going to be the ratio of our leading coefficients. So the leading coefficient in the numerator is 9, and the leading coefficient in the denominator is 3. So y equals a sub n divided by a sub m, which is 9 divided by 3, which equals 3. So our horizontal asymptote is going to be the line y equals 3. Excellent. All right. We are asked to find the horizontal or oblique asymptote for this graph, for the graph of this function g of x, where g of x equals 10x to the fifth minus x cubed plus 2 divided by x cubed minus 1. So we can see here that we have our graph, and from this graph we can see here that there is no horizontal or oblique asymptote, but let's confirm that. So p of x has a degree of 5. Q of x has a degree of 3. So n equals 5 and m equals 3. So n is greater than or equal to m plus 2, where n is 5, m is 3. Okay, so 5 equals 5, and that's true. So that means our graph is going to resemble y equals a sub n divided by b sub m times x to the n minus m. Okay, so the leading coefficient in the numerator is 10. In the denominator, it's 1. N is 5. M is 3. So that equals 10x squared. So our graph is not linear. Okay. And it's going to resemble 10x squared, the graph of 10x squared. Okay. But we know that there is no horizontal asymptote or oblique asymptote here. Okay. All right. Excellent. And that concludes 3.5.